Hello guys and welcome back. Before we talked about DC motors, how they're built, today we're going to talk about how can we control them, or the control methods. First, across the line starting method. Small DC motors can be connected directly across the line for starting method because of a small amount of friction and inertia is overcome quickly in gaining full speed and developing a counter EMF. Magnetic across the line control of a small DC motor similar to AC control or to 2 or 3 wire control. Some DC across the line starter coils have dual windings because of the added load of multiple break contacts and the fact that the DC circuit lacks the inductive reactance which is present with AC electromagnets. Both windings are used to lift and close the contacts, but only one winding remains in the holding position. The starting or lifting winding of the coil is designed for momentary duty only. Assume that the coil M, for example, is energized momentarily by the start button. When the starter is closed, it maintains itself through the normally open maintaining contact, or M. And the upper winding of the coil, since the normally closed contact M is now open, power contacts M close, and the motor starts across the full line voltage. The double break power contacts are designed to minimize the effects of arcing. DC arcs are greater than those due to alternating current. For example, see the following image, and it shows another control method used to start a DC motor. In this method, a current limiting resistor is provided to prevent coil burnout. It's used to eliminate continuous duty current flow to some coils, or when the coils are overheated. The coil first receives the maximum current required to close the starter. It then receives the minimum current necessary to hold it in contacts and for continuous duty through the current limiting resistor. Next is definite time starting control. When large DC motors are to be started, current inrush to the armature must be limited. One method of limiting this current is to connect resistors in series with the armature. When the armature begins to turn, counter EMF is developed in the armature. As counter EMF increases, resistance can be shunted out of the armature circuit, allowing the armature to turn at a higher speed. When the armature speed increases, counter EMF also increases. Resistance can be shunted out of the circuit in steps until the armature is connected directly to the power line. Limiting the starting current of the armature is not the only factor that should be considered in a DC control circuit. Most DC motor control circuits use a field current relay, or FCR, connected in series with the shunt field of the motor. The field current relay ensures that the current is flowing through the shunt field before voltage can be connected to the armature. If the motor is running and the shunt field opens, the motor will become a series motor and begin to increase rapidly in speed. If this happens, both the motor and the equipment it is operating can be destroyed. For this reason, the shunt field relay must disconnect the armature from the line if shunt field current stops flowing. In the following image, you can see a DC motor control with two steps of resistance connected in series with the armature. When the motor started, both resistors limit current flow to the armature. Time delay relays are used to shut the starting resistors out of the circuit in time intervals of 5 seconds each until the armature is connected directly to the line. The circuit operates as follows. When the start button is pushed, current is applied to relay coil F, and all F contacts change position. One F contact is connected parallel to the start button and acts as a holding contact. Another F contact connects to the field current relay and the shunt field to the line. When the shunt field current begins to flow, contact FCR closes. When contact FCR closes, a circuit is completed to the motor starter coil M and coil TR1. When the starter M energizes, contact M closes and connects to the armature circuit to the DC line. 5 seconds after coil TR1 energizes, contact TR1 closes, allowing current to flow to relay coils S1 and TR2. When contact S1 closes, resistor R1 is shunted out of the circuit. 5 seconds after relay coil TR2 energizes, contact TR2 closes. When contact TR2 closes, current can flow to coil S2. When contact 2 closes, resistor R2 is shunted out of the circuit and the armature is connected directly to the DC power line. When the stop button is pushed, relay F de-energizes and opens all F contacts. This breaks the circuit to start a coil M, which causes contact M to open and disconnect the armature from the line. When coil TR1 de-energizes, contact TR1 opens immediately and de-energizes coils S1 and TR2. When coil TR2 de-energizes, contact TR2 opens immediately and de-energizes coil S2. All contacts in the circuit are back in their original position, and the circuit is ready to be started again. Next, solid state DC motor controls. Solid state DC motor controls. Direct current motors are used throughout much of the industry because of their ability to produce high torque at no speed, and because of their variable speed characteristics. DC motors are generally operated at or below normal speed. Normal speed for a DC motor is obtained by operating the motor with full rated voltage applied to the field and armature. The motor can be operated at below normal speed by applying rated voltage to the field and reduced voltage to the armature. When resistance is used for speed control, much of power applied to the circuit is wasted in heating the resistors, and the speed control of the motor is not smooth because resistance is taken out of the circuit in steps. Speed control of a DC motor is much smoother if two separate power supplies, which convert the AC voltage to DC voltage, are used to control the motor, instead of resistors connected in series with the armature. For example, in the next image, notice that one power supply is used to supply constant voltage to the shunt field of the motor, and the other power supply is variable and supplies voltage to the armature only. The shunt field power supply. Most solid-state DC motors controllers provide a separate DC power supply, which is used to furnish excitation current to the shunt field. The shunt field of most industrial motors require a current of only a few amps to excite the field magnet. Therefore, a small power supply can be used to fulfill this need. The shunt field power supply is generally designed to remain turned on when the main armature power supply is turned off. If power is connected to the shunt field even when the motor is not operating, the shunt field will act as a small resistance heater for the motor. This helps prevent moisture from forming in the motor due to condensation. The armature power supply. The armature power supply is used to provide variable DC voltage to the armature of the motor. This power supply is the heart of the solid-state motor controller. Depending on the size and power rating of the controller, armature power supplies can be designed to produce from a few amps to hundreds of amps. Most of the solid-state motor controllers intended to provide the DC power needed to operate larger DC motors convert three-phase AC voltage directly into DC voltage with a three-phase bridge rectifier. The diodes of the rectifier, however, are replaced with SCRs to provide control of the output voltage. The next image shows SCRs used for this type of DC motor controller. A large diode is often connected across the output of the bridge. This diode is known as the freewheeling or kickback diode and is used to kill inductive spike voltages produced in the armature. If armature power is suddenly interrupted, the collapsing magnetic field induces a high voltage into the armature windings. The diode is reverse biased when the power supply is operated under normal conditions, but an induced voltage is opposite in polarity to the applied voltage. This means the kickback diode will be forward biased to any voltage induced in the armature. Since a silicon diode has a voltage drop of 0.6 to 0.7 volts in the forward direction, a high voltage spike cannot be produced in the armature. Voltage control. Output voltage control is achieved by phase shifting the SCRs. The phase shift control unit determines the output voltage of the rectifier. Since the phase shift unit is the real controller of the circuit, other sections of the circuit provide information to the phase shift control unit. Field failure control. As stated previously, if current flow through the shunt field is interrupted, a compound wound DC motor will become a series motor and race to high speeds. Some method must be provided to disconnect the armature from the circuit in case current flow through the shunt field stops. Several methods can be used to sense current flow through the shunt field. A current relay can be connected in series with the shunt field. A contact of the relay can be connected in series with the coil of a motor starter used to connect the armature to the power line. If current flow were stopped, the contact of the current relay will open, causing the circuit of the motor starter coil to open. Another method used to sense current flow is to connect the low value or resistance in series with the shunt field. The voltage drop across the sense resistor is proportional to the current flowing through the resistor. Here's where our Ohm's law applies. E for voltage equals I for amps times R for resistance. Since the sense resistor is connected in series with the shunt field, the current flow through the sense resistor must be the same as the current flow through the shunt field. A circuit can be designed to measure the voltage drop across the sense resistor. If this voltage falls below a certain level, a signal is sent to the phase shift control unit and the SCRs are turned off. Current limiting control. The armature of a large DC motor has a very low resistance, typically less than 1 ohm. If the controller is turned on with full voltage applied to the armature, or if the motor stalls while voltage is applied to the armature, a very large current will flow. This current can damage the armature of the motor or the electronic components of the controller. For this reason, most solid-state DC motors controls use some method to limit the current to a safe value. One method of sensing the current is to insert a low value of resistance in series with the armature circuit. The amount of voltage dropped across the sense resistor is proportional to the current flow through the resistor. When the voltage drop reaches a certain level, a signal is sent to the phase shift telling it not to allow more voltage to the applied armature. When DC motors of about 25 horsepower or larger are to be controlled, resistance connected in series with the armature can cause problems. Therefore, another method of sensing armature current can be used. In the next image, you can see in this circuit current transformers are connected to the AC input lines. The current supplied to the rectifier will be proportional to the current applied to the armature. When a predetermined amount of current is detected by the current transformers, a signal is sent to the phase shift control, telling it not to allow any more voltage applied to the armature or to the phase. This method of sensing armature current has the advantage of not adding resistance to the armature signal. Regardless of the method used, the current will control signals, the phase shift control, and the phase shift control limits the voltage applied to the armature. Speed control. The greatest advantage of using direct current motors is the variable speed characteristics. Although the ability to change motor speed is often desirable, it is generally necessary that the motor maintain a constant speed once it has been set. For example, assume that a DC motor can be adjusted to operate at any speed from 0 to 1800 RPM. Now, I assume that the operator has adjusted the motor to operate at 1200 RPM. The operator controls are connected to the phase shift control unit, as seen on the next image. If the operator desires to change the speed, a signal is sent to the phase shift control unit, and the phase shift control allows the voltage applied to the armature to increase or decrease. DC motors, like many other motors, will change speed if the load is changed. If the voltage connected to the armature remains constant, an increase in node will cause the motor speed to decrease, or a decrease in node will cause the motor speed to increase. Since the phase shift unit controls the voltage applied to the armature, it can be used to control the motor speed. If the motor speed is to be held constant, some means must be used to detect the speed of the motor. A very common method of detecting motor speed is with the use of an electrotachometer. An electrotachometer is a small permanent magnet generator connected to the motor shaft. The output voltage of the generator is proportional to its speed. The output voltage of the generator is connected to the phase shift control unit. If node is added to the motor speed will decrease. When the motor speed decreases, the output voltage of the electrotachometer drops. The phase shift unit detects the voltage drop of the tachometer and increases the armature voltage until the tachometer voltage returns to the proper value. If the load is removed, the motor speed will increase. An increase in motor speed causes an increase in the output voltage of the tachometer. The phase shift unit detects the increase of tachometer voltage and causes a decrease in the voltage applied to the armature. The electronic components respond so fast that there is almost no noticeable change in motor speed when load is added or removed. As always, thank you so much guys for watching, and please like, share, and subscribe. And feel free to comment or send me any suggestions. Thank you. See you in the next one.